Yes. So, can you all see me? I will try to move this so that you don't have that. Okay. Thank you, Fang, for inviting me to this. I will talk a bit about additive manufacturing of stainless steel 316L and try to emphasize productivity and how to kind of address that and increase productivity, since this is one of the main challenges that we see today to try to push this technology into industry. But before going into that, I will just give a very brief introduction. As many of you have seen these kind of presentations before, and additive manufacturing is on a hype, so I will just briefly kind of narrowing down what type of additive manufacturing techniques that I'm working with. So it's the laser powder bed fusion. So we use a powder and a high energy laser beam, and then we melt the powder and make complex shaped parts. And the benefits with doing this is that we can increase part performance by making the design more complex. We can increase the process efficiency and also reduce the time to the market, reduce material waste, and also introduce new designs, as we are no longer limited by the process. It's rather our thinking that are limiting how we are designing the components. So if we benchmark additive manufacturing, we can say that for conventional methods, we have a cost increase when we increase the complexity. This is something that we don't see in additive manufacturing, where the cost is basically the same. On the other hand, we have a quite slow process. So we can't produce millions of parts per year, or even 10,000 of parts could be problematic. So we need to have a complex part that needs to be produced in lower volumes. And then we are limited in the part size. And that is basically today the build chamber. So we don't have any technical limitations, or don't have any major technical limitation in part size. But today we are talking about maybe 30 by 30 by 30 centimeters, which will limit how big parts we can do. So to conclude this, you can say that laser powder bed fusion should be used for complex part in low production volumes. And here it starts to kind of narrowing down which type of industries that this could be interesting for. And then we have medical implant, aerospace, and tool applications, and so on. So we are trying now to expand this, to increase the productivity so much that we can address like automotive and other industries, so that they can see a benefit in using additive manufacturing. So everything starts with the powder. I will not go into detail, but this powder needs to have a quite high quality when we talk about metal powder. It's highly spherical. It needs to be quite smooth surfaces, low amount of satellites. All these quite high demands increase price. This is something that I will not go into detail in this presentation, but if we can use a cheaper powder, we can actually gain quite a lot of, or reduce the cost quite a lot, and also powder recycling. So it's good to keep this in mind when we talk about productivity. I will mainly talk about productivity in terms of what we do with the machine and so on, and not the powder itself or the raw material. So the process that I have used is an EOS M290 machine. It's one of the brands that are most developed and used in industry today, together with the SLM solution. Within this machine, we have over 200 different parameters that we can change, which means that we can't address them all. But we have focused on 4 main parameters, and that's scan speed, hatch distance, layer thickness, and power. And those have shown to be the ones that are affecting the quality of the part the most. So that's also kind of why we focus on this. So we have a high energy laser beam, and we're creating a melt pool. And then this melt pool is moved around on the powder bed, and we are melting, creating a melt pool. And this melt pool will change in shape and also size depending on how we are selecting the process parameters. And depending on which cross section we are using, I will see if I can get the laser point, it will appear differently. So if we take like a light optical microscope image, we can see here that each of these kind of features can be observed in the microstructure. So this is important, as this will determine later on the mechanical properties of the part, how this microstructure looks like. And as you might understand now, that if we change the process parameter, then we will change the melt pool shape and the melt pool size, meaning that we will affect both quality and mechanical properties of the part. So now we have talked about the laser, and now we're talking about how we are moving that laser. So once again, here we have maybe 10 different types of scanning strategies and scan rotations and so on. What I want to highlight here is that we use a pre-developed scanning strategy known as stripe scanning, which has shown to create a high quality part with very few defects and with low residual stresses, which could be the case when you're using this technique, that you have very high residual stresses. But we have reduced that to a minimum by using this kind of scanning strategies together with the scan rotation. So this high energy laser beam creates a very complex microstructure consisting of large elongated grains that grow along the building direction. And those are separated by high angle grain boundaries. Inside those large grains, we have something known as a cellular structure or subgrains, and they are in maybe 0.5 to 1 micron in size. And inside those cells, we have precipitates and inclusions and oxides and so on. And as you can see, we have a microstructure ranging from millimeter and down to nanometer in the same material. And all of this will then influence the mechanical properties. So here we have a tensile test, meaning that we create the tensile test bars, and then we pull it until it breaks, and then we measure how much it can withstand. Here we compare it to a cold rolled, conventional manufactured 316L, and as you can see, we have a very increased yield strength. The yield strength is where the curve starts to bend. As you can see, it's increased quite a lot. Whereas down here, you can see that the UTS value, it's almost the same, but we have a reduction in elongation instead. So we can create a material that has better or at least comparable mechanical properties to conventional methods. If we would compare this to a cast material, our mechanical properties is much, much better, which is very beneficial. So this kind of wraps up the introduction. So now we will talk a bit about productivity. But before going into this, I would like to just narrow it down to saying that we need to consider both the microstructure and the mechanical properties and the productivity. It doesn't make sense to say, okay, I want as high productivity as possible, because then you would need to reduce something else. Then your mechanical properties will be not good enough. So what we are aiming here is to kind of making a defined quality. We want to not have as good mechanical properties as possible. We don't need, maybe for a certain application, to have super high yield strength. Maybe we can reduce that, but instead gain in build speed and productivity. So what we are trying to do is to find a correlation between these three corners, if you like. How is productivity affecting microstructure, and how is microstructure affecting mechanical properties, and so on, trying to find how can we create a part with a defined quality that fulfills the needs that this specific part needs. So one way to do that is to change the process parameters. And changing the process parameter will mainly affect the build speed, which is the limiting factor. We're talking about a very slow process. So if we can increase the build speed, then we can reduce the cost and also produce more parts per year, for example. One way is to evaluate this is to use something known as the energy density function. It's not important the specific components, but just knowing that we have a correlation between scan speed, layer thickness, and power, and so on. So what we did was that we changed scan speed, 3 different, and then hatch distance, 3 different there as well. And as you can see on the microstructure, up here we create a very strong preferential orientation of the grains. This is EBSD maps. So we have a strong 101 texture, whereas down in this corner, we have a more random orientation with much smaller grains. So this is within the same machine. I'm just changing the process parameters. If we then look at the density, or the amount of pores and defects that we have in the materials, we can see that, okay, this one that has the lowest energy density, the lowest E, is having a density close to 98.8. It was actually 98.7. This, even if the drop looks very drastic, is still a very high density. If you compare to casting, for example, a cast component can have everything from 95 up to 99. But so this is still quite okay for being a stainless steel. But as you can see that moving up to this region, it more or less stabilizes, and we have almost a fully dense component. So here you can see how the defects looks like. So we have the black dots here are pores, and they are mainly because we are not putting in enough energy into the materials. We can't actually fully melt the powder particles. If we then look at the mechanical properties, once again, this is tensile testing. We can see that the yield strength and the UTS values are quite similar. We don't see any specific trends or anything like that. It's consistent. We are well above the recommended value for this, regardless of which parameter sets that we have used. The only thing that is seen is that the elongation is dropping quite a lot when we're using the lowest energy, 58. And that is because of the defects that we saw in the previous, this material here. So all these defects makes the material to be a bit more brittle. Even if brittle is the wrong word, it's still very, very ductile. 30% is more than enough to be used in any engineering application. But come back to productivity then. If this is the standard process parameters, which is in this region here, we have an increased build speed by 20% by using the energy density of 58 instead. So just by adjusting scan speed and hatch distance, we can actually achieve a 20% faster build speed, which can save quite a lot of money. And this was just a pre-study showing, can we do it like this? Can we address this problem by changing the process parameter with aims that are not to have as high mechanical properties and as possible, but instead address it like, can we get enough properties and by that increase the productivity? Another way to increase productivity is to increase the layer thickness. The layer thickness is how thick each powder layer that we are spreading over the part. So standard is 20 microns. And if we would increase that to 80 microns 4 times, it means that we can increase the productivity 4 times. So in this study, we saw that, okay, the 80 micron, we see a reduction in yield strength. You have it here, but it's still very high compared to what the standard requires us. You see 170 is the standard and we are at 464. So we're still well above that. And we see a reduction in elongation for the 80 micron layer thickness, but still we can produce now a sample that is comparable to the 20 micron by developing new process parameters with the aim to increase productivity, instead of, as we did before, develop the process parameter to have as high quality as possible. We have done a case study together with Alfa Laval, where we produced this flow connector. The reason is that this flow connector is casted today, but the casting process is quite difficult. There are only one casting company that can produce this today, and Alfa Laval would like to see if this component could be 3D printed instead. But using the machine in what that we have here at Chalmers, 9 parts would take 19 days to produce. If we instead use the new 80 micron process parameter, we reduce that to 4.5 days. I mean, I think Alfa Laval would like to produce this part in terms of hundreds of components per year. So we are still quite high in process time, but this is for one machine. If you would have 2 machines or 3 machines, then you can produce more samples. But this kind of highlights why we need to address the productivity part. I mean, 19 days for 9 parts, that's too long. I actually have the part here, so it's quite big. It's larger than what you usually see in additive manufacturing. The next step in this case study was to address something more suitable, or they had other requirements depending on location of the part. So what we did was that we divided the part into different sections where the demands were different. So at the lower part, there were no actually forces. They didn't have any needs for any specific elongation or so on. And here, they needed to have lower energy because the design looks like this. When we're going from thick to thin, we need to use a lower energy. Otherwise, we overheat the part and we get problems with the machine, so to say. And then up here is the critical, where we need to have the highest possible properties. So then we used some improved properties. By doing this, we can actually design our process parameter based on the load case. So we can adjust the process parameters depending on how the component will actually be used, and thereby have different mechanical properties, different build speeds depending on how the part will be used. So then we ended up in a build speed of around 250 hours with this optimized process parameters. So coming to the summary, we can adjust the build speed and the productivity by adjusting both the hatch distance scan speed, and we can also change other process parameter to improve the productivity. And one of the best way is to increase the layer thickness, and by that shortening the build time by a factor of 4 without reducing the mechanical properties. And these are the companies that I've been collaborating with and the funding that I have received for this kind of research. And with that, I would like thank you for your attention.
Yeah, thank you, Alex. Very nice work and great presentation. Any questions from the audience regarding Alex's presentation? Yeah, that is on additive manufacturing, which is attract a lot of attention in recent years.
I have one fund.
Oh, yes, great. Yes,
because
please.
you were talking about productivity. Doesn't this also link to energy consumption?
For sure.
Save a lot of energy? I mean,
yes.
Maybe that's the argument to use.
Additive manufacturing. Yeah. I mean, if we can produce a net-shaped part that we don't need to machine, and we can reduce the waste material, so to say, then we will save energy as well. But you can also make an argument, which we haven't started looking into, how much energy are the machine actually using? Like,
yeah, because that would be another thing. It's not just productivity could be measured in build time, but it could also be measured in terms of energy consumption. Yes. So I guess the energy map here would be very interesting to see. Maybe you're saving masses of energy to produce that part.
Yes,
I don't know.
It's a complicated question, because if we change, for example, the energy input, the power of the laser, sure, the energy consumption will go up.
Yeah, but if you're using less hours, maybe you're saving energy.
Yeah, exactly. So we need to. There is actually equipment now that you can put on the machine, which measures how much energy are you actually using while building this, and then you just translate that to like cubic centimeters per energy or something like that.
I think you already have the numbers, don't you? Because you're controlling that energy input.
Yeah, but that is not the energy consumption. That is the energy that is absorbed by the material.
Oh yeah, but you have the power of the laser. Isn't that the main energy source?
Yes, but then we have a vacuum pump, which continuously consuming.
True.
So for sure, this is something that should be addressed, and that's also interesting for industry to know, to calculate an accurate cost for the part. They want to know, okay, how much will this part cost in the end? And then energy can be quite important.
Because if I link back to the previous speaker here, it depends on where you make it. So what's the energy mix? So you can convert that to CO2 equivalents.
Yes.
I think that's a nice number to have.
Yeah.
That would say, make everything in Sweden.
Yeah.
or in northern Sweden.
Yeah, exactly. Yeah. And then you have the cooling as well.
Yeah, exactly. Thanks.
Yeah, thank you.
Yeah, thanks, Dan. But I have one quick question. When you try to optimize the parameter different parts, you use different parameters in order to save, to increase productivity, and also at the same time save energy. Will that introduce some internal stress or something between different parts?
It could. The residual stresses is depending on, of course, the process parameter, but mostly on the size of the part. If you have a really thick and bulky part, that would introduce more stresses than a thin component. The process parameters that I have been working with so far have not shown any sign of having high residual stresses or too high residual stresses. But of course, that could be something that you need to be aware of when optimizing. The tricky part is how to measure residual stresses on AM parts. There is no good method to do that as of now, because we have so rough surface. So an XRD method or any X-ray method would give a quite large scatter.
Okay. Great, thank you so much. Are there any other questions for Alex? Yeah. Otherwise, I think we thank the two speakers for today again. And next seminar will be in October. September. 23rd of September, and then there we will have two former PhD students who has gone to industry and worked for some years and come back to share their work for the moment, and also maybe share their experience of their career. So hope to see you all there in 23rd of September. Thank you. Bye-bye.